In this video, we'll be using Maxwell's construction in order to plot a two-phase envelope that is superimposed on the PV isotherms that we created in an earlier video. This is Maxwell's construction, where it basically entails that these two different areas, one under the pressure and one above the indicated pressure, are equal to each other. And we will be working on plotting this into our Python code according to the three different volumes that we received from our previous video. These three different volumes are these three individual points on the on this Maxwell construction, and we'll be using them to create our code. Alright, so let's get started. Well, real quick before we actually get into the nitty-gritty, I want to show you guys really quick that I added two quick lines of code. I imported two different functions, quad and root, which we'll be using later on. Root we've used before many times, and quad is a new function that will help us accurately find the area under point, which is what we're trying to find, right? So let's start off with that. Let's start with finding the area. Let's create a function that let's call it area, and it's going to be dependent on pressure and of temperature, right? Alright. And then the next thing we want to do is that we want to create an integral, right? We want to create an integrand. So we'll do define integrand, and it is going to be based off of v. And then what we want to return from this function, what we want to get is the difference in pressure, right? We want to kind of get the y-axis, right? So what we're going to do is we're going to return the pressure minus the cubic pressure equation that we solved up here, right? This one right here, cubic underscore p for volume temperature, right? We're going to copy that, put it down here. So that's what we're going to return, right? So that we have that. Now, looking back to our main function of area, we're going to want that to return this is where the earlier function that I was talking about, the quad, comes in. And what we're going to use is we're going to use the integrand, and we're going to use v1 and v2 from the first point to the second point, right? v1, v2, right? As well as the quad, the integrand of v2 to v3 now, right? Because we want the middle point and the rightmost point, right? So you're probably asking, how do we find v2, v1, v3? Well, we actually already know what they are, right? If we look right above us, we have these three values, which we found from this equation, which are the three different volumes, right? v1, v2, v3, right? So what we do is we call v1 v2 v3 is equal to the cubic equation that we've made with volume, which is dependent on pressure and temperature. Right. Shift enter, we run this through. The small error there was just I just needed to add to a small tab here and here. So we run this through and it's all good now. So let's check to make sure that this function is all good. So let's get an example. Let's call it area, and let's say the pressure is let's say, I don't know, 10 times or 1 times 10 to the 4th, and then temperature, say 500 Kelvin. Press shift enter. There we have it. We have we're given 4 different values, right? And this first value and this third value are the ones that we're interested in. And as you can see, they are kind of opposites of each other, and that's how we're trying to optimize and what we're going to figure out. And these other two numbers are just simply the error within this, so we don't really care about this. So just to take this off, I'm just gonna index on both of them, shift enter, and there we go. We are only given those two values. So now that we know that this function is good, we can use it to create another function, right? And I'm just gonna call this function the difference of area, so area underscore difference, right? And it's going to be depending on vectors, right? We're going to have many different values going through it. It's going to be dependent on vector and on temperature, right? And so we have an array here of many different pressures, and we want to make sure that the pressure is run through there. So basically vector, and we put the first or zero index. And then with this, we now recall our earlier function area to use these two different values. So now what I'm going to do, I'm just going to call the first side left and right. So just call them left and right. So left and right is equal to the function area for depending on pressure and temperature. Right? And then what I'm going to want this function to return is we're going to want to make sure that it is equal to 0, right? Like we said before, these should be opposite each other, so we want to make sure that left plus right is equal to 0. So that's what our return is going to be. So here is where the root function comes into play. We're going to use it here. So we'll just start off by seeing if the area difference, the digital function that we just made, works. So we're just going to call it root, call the function we just made area diff. Right? And then for the vector, we need a vector to start off, right? And then we're just going to make a guess, right? Start off with 10,000 pascals, right? Why not? And then for the final, we need argumentatives, right? So which is the temperature in this case. So for now, I'm just going to go with 370 degrees, but for the argumentative, it just equals to ARGS equals, and then 370 degrees. Right? So shift enter. We get this whole list, and once again, we followed by period x, we simply get the array, and there it is, our value, or 80,636 pascals is the ideal. And so we know that this is the pressure, or the pressure due to the vapor in the vapor phase, right? So I'm just gonna make that, and what we're gonna do is just gonna work out, make a for loop so that we get infinite many values for. Before we actually started creating the for loop, I should add a few things. I want to create this argumentative simply to t, so that later on we are able to better influx it and so on, right? And if you still see, we still get the same values. But another thing that I want to do is create some new volumes, right? Like we did up here, we're going to have to create some new volumes for here. So what we're going to do is the volume in the liquid phase, volume in the intermediate, so it's the big line that we see, not in here, but I showed in previous videos, and the volume of the gas phase, right? that is all going to be equal to the cubic root that we made earlier, right? Again, pressure, temperature. Right. Now we can actually get started building our photo. So let's get started. So let's say for we'll call this x, right? For x, we call NP the line space. Right? And then what are we gonna want this for? Well, we're gonna start. For now, we'll just say we want from 0 to 10, and we want 50 different values, right? Now we're going to want this into for loop, right? Then we can also get rid of this temperature up here, right? And then, so now we want to create lists for each of these so that we can store each of these values, right? So we're going to have a list for the pressure, right? There's pressure. And then we're also going to have some for the different volumes, right? Volume and liquid phase, obviously. As well as the volume of the gas phase, as well as, right? And then we want to make sure that throughout our for loop that the values are added towards the end, right? So what we're going to do is going to append each of these lists, right? So P vapor for that, and then for the liquid phase, list append, for the gaseous phase, list append, you want line the gas phase, right? And so we're also going to want this part into our for loop, right? Right. And so, this pressure as well should be the new pressure, which is P vapor instead of the old pressure, right? This new equation is going to be depending on this, right? Then another thing that we want to make sure that is going to help us when we're plotting and graphing is our guesses. So for this, if we say, let's put in 275 or 275 Kelvin, the given values that we will receive will be the values equivalent to 280. And then let's say we put in 285, we would once again get the same values for 280, and this would keep happening. So one way we can change this is that we can change this to, in fact, let's say call it guess, right? And then up here, so we call the guess is equal to let's say 10,000 for now, right? But we're gonna want the gas to remain as similar as possible to the pressure that we calculated in the vapor pressure, right? So now we want to start plotting this stuff, right? So what we're gonna do is go back up into our code and simply copy and paste this whole thing, right? Go down here, copy and paste, but now I'm going to make a few differences. We're going to now make this figure 2, right? So that we do not confuse it with the previous figure. And we're going to go into here and just name this figure 1. Just make it help out a little bit more, right? So we run this through, we get a whole new graph, right? Then we want to add into a scatter plot, right? We want to add what we want to figure out, right? So fig 2 dot add scatter. Then the x-axis is going to be equal to the new list that we created. So v list. Right. Then the y-axis now is going to be the new p list that we created, right? And the mode that we're gonna want is still gonna be lines. Now we're gonna want to create a specific color since we want it to stand out, right? So the color of this would be black. So line underscore color, and we're gonna make it black. Right. Enter. So this is what we get, and we can see that we are given these values, but only the left hand side. So we often want to put create another list, right? Or we want to create another scatter, but this one instead of the liquid phase, we'll be using the gas phase, right? Shift enter, run that again, and we can see now we're getting some values on our right hand side too, right? But we're still having an issue with connecting these and getting values up to this temperature. So one thing we can do is we can come up here and mess with the temperature. We don't want this to go over the critical point, so that will be a mistake, but we can want to get there high enough so that we can connect this better. So we put in 630. Hopefully that works and it reads it. Now we shift enter and see the new graph that we're given. As you can see, it's starting to look a little bit better. Slowly connecting. Another thing we can do to help fix this out is to put all the two different lists that we have into a singular list, right? So we can go up here and we can make a v list is equal to as well as a p list. We already have a p list, so we're just going to do p underscore another p. Right. And so for the volume, it's just simply going to be the volume of the phase. Right. And it's going to be add volume of the gaseous phase, right? But something we want to make sure is we want to change the increment or change how it's going. So what we want is we want to make sure that it's going from start to finish and incrementing by -1, so that we fix that up. And the same for the pressure, we do p underscore list plus p underscore list. But the same thing there. We run that through, make sure it's all good, give its time, and then run through this and get our new plot. Well, actually now we can also, instead of plotting both of these, we can plot simply one, and instead of calling this PL list, we simply call it V list, right? So the P list is now PP. Right, we run this through again. Look at that. Now we are connecting the two lines together, but it's still having issues when the temperature is a little bit higher and it's not sure what to do. So I want to show you guys an idea now. So if we open up Desmos, graphing calculator, if we were to graph the exponential of x, this is what we get, right? So if we get the negative x, this is what we get the inverse, right? And now if we get the inverse of this whole thing, get a whole different thing, which is similar to what we want, right? As the numbers get higher and higher, the numbers get closer and closer together, right? Although this is not at 0, it is at -1. So if we add 1 to it, it is now at 0. And so let's say we want to create what we want. We multiply this whole expression, right? And we would multiply it by the temperature. So we know that the critical temperature of water is 647 degrees Kelvin, right, approximately. Then we'll subtract the starting value, which for now we'll say it's 2050, let's say 275 degrees, right? This is what we get now, right? So we get higher and higher, numbers get closer and closer, but we're not there yet, right? We're not at 647, we're not at the critical temperature of water. So what we want to do is now to this whole equation, we want to add the starting temperature, 275, right? So if we go all the way up here, you see that it has now reached its critical temperature, right? This is what we want for in our graph, right? So now we simply put this aspect of the equation into our collaboratory code, right? So let's do that. So we start off by, instead of using t, we now use a dummy variable, we'll just call it x. And these new functions will be going from 0 to 7, and we want a lot of points, a nice smooth curve, so we'll give it 500 different points, right? Then now we have to give a value for t though, right? So like we said, we have the critical temperature, so p dot tc, and then subtracted from 275, right? Then multiply that by, what do we say? We had 1 minus the negative x on it, so 1 minus, we have mp dot x of negative x, right? And then, right? And then from all of that, we add 275 back in, right? And then shift enter, make sure this is all good. And now we go down here and run this back again, and look at our new plot that we have. And would you look at that? There we go. As video, this now have a two-phase envelope superimposed on the different critical temperatures. So there we have it. Thank you.